SwayamPrabha. Digital India. Educated India.
So, good morning. Yesterday we started looking at fundamentals of how natural convective heat transfer occurs, and also we derived the governing equations and the non-dimensional form of the governing equations. We find that the more important term coming in the buoyancy force is the non-dimensional group, which is Grashof by Re square. So, this is important non-dimensional parameter which is governing basically the strength of natural convection with respect to the forced convection. So, the Reynolds number that we defined, you should remember when we non-dimensionalize that governing equations was such that we used Re is equal to Ur into L by mu. So, in this case the reference velocity Ur from the order of magnitude analysis, we have also expressed this as, do you remember what it is, G beta T wall minus T infinity into L, correct. So, essentially the velocity here what we are referring to is nothing but a velocity scale arising out of the buoyancy force. Okay. Now, there could also be a case where you can have a bulk motion along with the natural convection, you can also have a bulk motion. In that case you have to modify the definition of Reynolds number to the conventional definition where we define it based on the free stream velocity. Okay. So, however, still the same non-dimensional combination will be there, only that the Reynolds number in that case will be defined based on the bulk velocity. So, this is an important non-dimensional number, therefore, governing the strength of the natural convection to the forced convection. So, this is the ratio of your buoyancy force to the inertial force. Now, so you can have, considering therefore two scenarios where you can have the forced convection acting vertically upward or going downward. Okay. So, we call this case where the buoyancy and the direction of the bulk motion are in acting together. So, this is called buoyancy aided natural convection, or buoyancy aided you can say forced convection. Okay. So, these are two different scenarios in mixed convection. Okay. So, one is a buoyancy aided convection, the other is a buoyancy opposed convection where the buoyancy is in this case is trying to act upward because the wall temperature is greater than the free stream temperature. However, the bulk motion is acting downward. So, in fact, depending on the strength of the forced convection, the boundary layer growth could be either way. So, if your forced convection dominant, then the boundary layer will actually start growing from top to bottom in this case. Okay. So, this is decided by the ratio of Grashof number to Re square. So, if this strength is around 1, then both of them will be equally dominant. If this is very small, then Reynolds number will be the dominant one, and therefore, you might actually end up having a boundary layer growing in this way. So, depending on this, if you draw the velocity profile, so unlike the pure natural convection case, you will have a finite value of velocity profile at the edge of the boundary layer, and this should approach your u infinity, right. So, you do not have actually minima at this point, it will be a finite value depending on what the u infinity is, and this will vary. So, if your u infinity is considerably large, you can actually end up with actually going for a gradual profile, and then which will approach your conventional boundary layer velocity profile. okay, without going through the maxima and then approaching U infinity. It depends on the strength of the forced convection in this case. Nevertheless, now you can use the same set of governing equations that we derived yesterday, and we can find the solution for the mixed convection case also. However, one of the more simpler approaches in the empirical manner will be to find the Nusselt number independently for forced convection and then natural convection, and then simply blend these two values together depending on whether it is a buoyancy assisted case or a buoyancy opposed case. So, for the case of buoyancy aided one, you see that the boundary layer growth is much faster and it is thicker than the case of buoyancy opposed. Okay. So, therefore, when you look at the sign, it can be either plus or minus depending on you have a buoyancy assisted or a buoyancy opposed case. So, now the value of m here depends on the kind of configuration. So, I will just list out the value of that index m for a few cases, for a few configurations. For example, if you have a vertical plate and you have an so this index m will be something like 3.5. Okay. So, this is usually between 3 and 4. Okay. So, this value is generally taken to be 3.5, and if you have a, for example, a horizontal cylinder also, this value, if depending on the condition, boundary condition, if it is a constant wall temperature, this is again taken to be 3.5. The same horizontal cylinder with constant wall flux is taken to be 4, and similarly for a sphere also with a uniform surface temperature, this value is taken to be 3.5. Okay. So, depending on the configurations, you can use the values of m appropriately and blend the values from the independent results. So, usually it is between 3 and 4. Okay. So, now what we will do is that, so I just also will give a representation of how the Nusselt numbers might probably look in the buoyancy assisted case. So, when we plot Nusselt number as a function of Re for a fixed value of Grashof number. So, that is, I maintain say the Grashof number to be something like 10 power 5 and vary only the Reynolds number. Okay. So, I can go anyway from therefore, natural convection regime all the way to forced convection regime depending on the value of Reynolds number that I vary. Okay. So, for very low values of Reynolds number, so then what happens? This will be in the natural convection regime. So, typically you end up with value for natural convection. Now, this will be your natural convection value. So, you see what happens at low Reynolds numbers, since it is dominated by buoyancy, irrespective of what the Reynolds number is, the Grashof number is also a constant. So, the Nusselt number will remain a constant, it will be governed by the value of Grashof number that you use. Now, when you again go to very high value of Reynolds numbers, so then the buoyancy will be insignificant compared to the inertial force, and therefore, Nusselt number will be purely dictated by the forced convection. In forced convection case, Nusselt number is directly proportional to Reynolds number, and therefore, it progressively increases in the case of forced convection. So, if you plot forced convection case, you will have something like this. So, this is your forced convection case. So, therefore, the combined convection will have to transition from the natural to the force like this. So, this will be your combined or mixed convection. So, this is the assisted case. So, initially when you talk about low Reynolds number, so you have only natural convection which is governing the value of Nusselt number. Very high Reynolds number, it is only the forced convection which is governing it, and in between where the ratio of Gr by Re square is of the order of 1. So, you have both of them, both the forced convection as well as the natural convection. So, your Nusselt number values will be transitioning smoothly from the natural to the forced convection. Is that okay? So, this is a kind of more realistic case. In many applications you can actually have both the forced and natural convection to be equally significant, and we cannot therefore neglect the effect of mixed convection in those cases. So, now what we will do is first we will take up the pure natural convection case where we do not have any bulk motion, and try to look at some solutions to the fluid flow and heat transfer problem. So, what are the different ways of solving it? Just like you have your external forced convective boundary layer, for which we have the Blasius and Polhausen solution, we can approach by using similarity methods. So, similarity solutions are the exact solutions that we are going to do, and once again these can be done for either a constant wall temperature boundary condition or a constant heat flux boundary condition. So, the constant wall temperature boundary condition case was originally attempted by Polhausen along with the external forced convection boundary layer. He also started looking at the case of natural convection, and he derived the similarity equation for this case also, but this was later on solved for wide range of Prandtl numbers by another person called Ostrach. Okay. Originally during Polhausen's time there were the numerical methods were very few. So, he could not find a very general solution for the Nusselt number for different Prandtl numbers. So, only for a fixed Prandtl number he was able to get the solution, but nevertheless that similarity equation was solved using numerical methods later on by Ostrach, and he generalized to a different range of Prandtl numbers. And the other solution is for the constant heat flux boundary condition, and this was done by two people, Sparrow and Gregg. So, this is extension to the basic Polhausen's solution to a constant heat flux boundary condition, and apart from this you also have the approximate methods. So, one is the use of similarity solution, the other is the approximate technique, which is not as rigorous, but nevertheless gives you very useful correlation which is close to the exact solution. So, the approximate method has been derived by a person called Squire. Okay. So, using the momentum and energy integral technique, especially for the constant wall temperature boundary condition. Okay. Later on people extended the solution to also constant heat flux boundary condition. So, like this similar to the external forced convection, you have similarity and approximate solutions also for the natural convection problem. So, we will start with the similarity solution with constant wall temperature boundary condition, okay, and later on we will move to the modification required in the similarity variable for the constant heat flux, and then we will go to the approximate methods. Okay. So, the similarity solution was originally developed by Polhausen, the similarity equation as such. So, we will look at the solution first before we go to the other extensions. Okay. Now, just the same with Blasius equations, you have to first start with defining a similarity variable, a similar transformation from xy coordinate to coordinate which is called the similarity variable coordinate. So, we do not know what is it, but let us say that eta will be a function of y by some delta, right. So, we will go on the same lines as Blasius did, okay, naturally, because we are talking about boundary layer growth, and therefore, the similarity variable should be able to map the boundary layer thickness at different x locations, and when you plot y by delta, this should be a similarity variable which should collapse all the velocity profiles, okay, the same starting point as the Blasius solution. But in this case, we do not know what the order of delta should be. What was the similarity variable in the case of Blasius equation? In the case of Blasius solution, the similarity variable was assumed to be y by x Rex to the power half, because delta, the order of magnitude of delta was found out to be x by square root of Reynolds number, local Reynolds number. Okay. So, now we have to find a similar transformation in the case of natural convection, that we have to replace Reynolds number with our Grashof number. Okay. So, yesterday we have seen that the equivalence between Reynolds and Grashof number. So, according to this non-dimensional number, we have Grashof number to the power half is of the order of Reynolds number, correct. So, therefore, if you want to use Reynolds number to the power half, this will be Grashof number to the power 1/4. So, what Polhausen did was to simply,
so that post convection graph is there.
Yes.
That Nusselt's number should be proportional to Re raised to 1/2 for post convection, right?
right.
It has to come like this graph.
So, it is Re raised to 1/2, this is going a square.
Square.
Yeah, that is correct. So, in that case we may, yeah, I mean this is a generic representation, yeah, but you can plot it exactly, you know, I have just given an idea here, the shape of the curve could be different. Okay. So, what you are suggesting is it should go like this, right. Okay.
And also the combination, it should be just shifted, that is the post convection curve should be shifted by distance of the natural convection. Why it is?
No, at very low values of Reynolds number here, so your Nusselt number with the forced convection will be very less. So, this will be insignificant. Okay. So, you are saying that this value should be shifted up here.
That is, the curve should be exactly shifted on above natural convection instead of Nusselt number equal to
No,
0.
but that is what I am saying. For very low values of Reynolds number, if you plot the value of Nusselt number from the natural convection, so this will be much larger than the forced convection value, right. So, this becomes dominant only after the Reynolds number becomes sufficiently large. This is a generic representation, okay. I am not plotting any values here. So, you can actually calculate it for fixing Grashof number say 10 power 5, you will find that this value will be different. For 10 power 6 this will again change, okay. So, but this is a generic representation saying that very low value of Reynolds numbers, okay, your forced convection contribution is small, okay. If you therefore put it into that empirical correlation, so it will be mostly governed by the natural convection value, and once you cross a threshold Reynolds number, then the forced convection becomes dominant. So, then that will be decided only by the forced convection value. So, in between these two is where you use this empirical correlation and blend both the values of forced and natural convection. So, that blending will give you a smooth transition, all right. So, let us come back to the solution. So, when we replace, therefore, Polhausen looked at the same similarity variable and therefore, he replaced Reynolds number with Grashof number. So, in this case, therefore, what happens? You have Grashof number to the power 1/4. Okay. So, this is of the order. So, what he did, you can also use this, find a similarity equation, solve it. So, it will not change the solution, but nevertheless to be precise he used Grashof number to the by 4 the whole raised to the power 1 by 4 is anyway a constant. This should not affect the final solution for say skin friction coefficient or Nusselt number, because everything will get adjusted in the end. Okay. So, even if you do not do this, you might get different constants in the similarity equation, but then finally when you calculate the CF and Nusselt number, they will get scaled proportionally, okay, by this constant, right. So, he used this as the similarity variable. Many of the textbooks in fact show that this is your exact similarity variable. There are few textbooks which omit the constant and they go ahead and solve, they get slightly different constants in the similarity equation, but finally the non-dimensional numbers all will be the same. Okay. In fact, the Blasius equation we did not use any of these constants. So, now the next step is to find the stream function. Okay. So, when we solve the governing equations, we have to solve in terms of the stream function, because then the continuity equation becomes redundant. Okay. So, therefore, what is the appropriate transformation for transforming the stream function, which is a function of x y, to another function which is only a function of the similarity variable eta. Okay. So, that is the next step that you have to find. So, how do we do that? So, once again we write down the equations for relating stream function and velocity field. So, u is equal to d psi by dy and v is equal to minus d psi by dx. So, let us take this particular relation and we can integrate it. So, therefore, psi will be nothing but integral u dy, and let us also assume that if you find the right transformation variable, then u by say u reference will be a function of only this variable eta, right. That is the purpose of finding the similarity variable. So, that finally when you plot u by u reference, so it will not vary as x and y, but it will all collapse as a function of eta, right. So, therefore, we can substitute for u into this. So, you have u reference which is taken out into g of eta. So, now we have to transform the variable y in terms of eta. So, we will write this as dy by d eta into d eta, correct, and dy by d eta can be expressed from the similarity variable here. Okay. Now, if you do that, I will just give you what will be the expression for psi. Please check that it comes out to be u reference times x by Grashof number to the power 1 by 4 into 4 raised to the power 1 by 4 into this integral g of eta d eta will be nothing but another function of eta, which will say f of eta, and this dy by d eta is nothing but x by x into 4 raised to the power 1 by 4 by Grashof number to the power 1 by 4, okay, and integral g of eta d eta is nothing but another function f of eta. So, therefore, this is your transformation from of the flow field from x y coordinate to an eta coordinate. This is your transformation from x y coordinate to eta coordinate through the similarity variable. So, this is your similarity variable and this is the corresponding transformation of the flow field. So, now that you have u reference, we also know that u reference can be related to g beta delta t. Okay. So, in fact, Polhausen gave he also introduced the constant 4 into this. It does not matter if you do not introduce any of the constants here or here also, finally it will not matter, all these are scaled up or down accordingly. So, the final non-dimensional numbers will not change, but let us do it exactly the same way he did it. So, if you substitute for u reference here and therefore combine the terms, you get 4 into Grashof by 4 power 1 by 4 into nu times f of eta. Okay. So, what we are doing is we are writing g beta into T wall minus T infinity in terms of Grashof number. Okay. Since we know the definition of Grashof number as g beta into T wall minus T infinity. So, this is a local Grashof number, we will define it with the local coordinate. So, I am just substituting for g beta into T wall minus T infinity as Grashof number into nu square by x cube into this, and already I have a Grashof number. So, I just combine the terms and finally, I will get this as my relation between psi and f. Okay. So, therefore, I find the transformation. Now, we can go ahead, proceed, start calculating u, then v du by dx, du by dy, all the derivatives, and then we can finally plug them into the governing equation. So, if this were the right similarity variable, so we should be able to transform this PDE into a similarity equation which is only a function of eta. So, that shows that we have whatever we have assumed for eta is correct. So, if you have some terms in x or y, that means we have still not found the right similarity variable. So, let us do that. The next step is therefore to find u, which is d psi by dy, and how do you find this? Now, psi is a function of y and we have to convert this in terms of eta. That means, we can write this as d psi by d eta into d eta by dy. Okay. The psi is a function of y through eta. So, now we will write d psi by d eta into similarity variable is a function of eta. So, this is a partial derivative d eta by dy. So, using the chain rule of differentiation. Okay. So, same way we can also calculate the v velocity. How do we calculate v velocity? Now, v velocity is nothing but minus d psi by dx. Now, if you look at this, psi is directly a function of x, correct, through Grashof number, and also function of x through eta. So, therefore, in this case we can write this as d psi by dx, this is your normal derivative with respect to x, plus it is a function of x through eta. So, therefore, this is d psi by d eta into partial derivative of eta with respect to x. So, this is exactly the same way we did the Blasch's solution. So, can you calculate and tell me what the velocities u and v are? So, when you write d psi by d eta, in this case the other terms are all constants, so only f is a function of eta. Okay. So, essentially you have 4 by into d eta by dy, which is nothing but 1 by 4 4 into 1 by x into Grashof number raised to the power 1 by 4. Okay. So, this gives my u to be 2 into Grashof number raised to power 1 by 2 into nu by x into df by d eta. Okay. So, we have 4 raised to the power 1 by 4 into 4 raised to the power 1 by 4. Okay. So, this becomes therefore 2 4 by 2, right. So, this is 2 and we have Grashof number raised to the power 1 by 4 into, so 1 by 4 plus 1 by 4. So, we have 1 by 2, okay, and then we have nu by x into df by d eta. Similarly, you can find v also. What I will do is I will write down the final expression here. You can, it will take some time, about 5 to 10 minutes to simplify and do this. You can check this a little bit later. So, it comes out to be minus 3 by 4 raised to the power 1 by 4 Grashof number 1 by 4 nu by eta minus okay. So, all you have to do is find d psi by dx, treating other things as constant and differentiating with respect to x. Then the second term you have df by d eta into d eta by dx. Okay. So, put together you have function of Grashof number x, nu and y. Okay. So, now using knowing therefore u and v, we can calculate the derivatives. Okay. So, we will see how the derivatives are calculated. So, therefore, the first step is du by dx. Okay. Now, how do you calculate du by dx? Now, you should tell me. So, again u is a function of x directly and also through eta. Okay. So, we can write this as therefore du by dx plus du by d eta into d eta by dx, right. Okay. So, du by dx, so you have to differentiate by keeping the other terms constant only as a function of x. Only with respect to x you should differentiate du by dx, the other is du by d eta. So, in that case the other terms are all constant. So, you have only d by d eta of df by d eta. So, you will have a d square f by d eta square term into d eta by dx, right. So, if you again substitute for d eta by dx and so on, so this should come out to be so when you write du by dx, that df by d eta will be a constant term. So, that will just come as it is, and from the second term you will have a d square f by d eta square. Okay. So, you have two one from du by dx and the other from du by d eta into d eta by dx, that is this term. So, where? Yeah. So, here when you differentiate you only treat the other terms as constant, right. Yeah, that is what. So, you have Grashof number to the power half by x. So, this is actually x power 3 by 2 minus 1. Okay. So, that is what 1 by 2. So, we have therefore 1 by 2 x power minus 1 by 2, right. So, this is what you are writing here. Again you are splitting that as therefore Grashof number to the power half by x square. So, here you have x power 3 by 2 minus 2, that is what minus 1 by 2, right. Okay. So, we are finally putting wherever possible in terms of Grashof number again. You do not want to carry that g beta delta t together. So, you are rewriting them in terms of Grashof number again, right. So, the next step is to calculate the gradient with respect to y. So, how do you calculate du by dy? So, u is a function of y only through eta. You look at the expression for u, right. We do not have any other term of y sticking there. So, therefore, we can write this as du by d eta into d eta by dy. So, now you should be able to tell me in terms of Grashof number what this is. This is much simpler term. So, you have Grashof number raised to power 1 by 4 into Grashof number raised to the power 1 by 2, 1 by 2, 1 by 4. So, what will be you should have 3 by 4, 3 by 4 and you have nu by x square into you have d square f by eta square. Okay. So, we can also find out the second derivative of velocity with respect to y. So, d square u by dy square. So, this is again the same way you can write this as what? You have du by dy, you already have du by dy. So, this will be a function of y only through eta. So, you can write this as d by d eta into du by dy into d eta by dy. Okay. So, that comes out to be Grashof number into nu by x cube into d cube f by d eta cube. Okay, please check once again. So, we have all this is constant, you have to differentiate with respect to eta, d cube f by d eta cube into d eta by dy. So, d eta by dy will again give gr x power 1 by 4 by x into 4 raised to the power 1 by 4. Okay. So, now that we have all the terms, what I ask you to do is please substitute into the x momentum equation. Okay. So, our momentum equation for this case okay. So, we can write the last term in terms of theta. We can now define for the constant wall temperature case T minus T infinity by T wall minus T infinity as theta, and therefore, we can write this as G beta into T wall minus T infinity into theta. Okay. So, you can go ahead and plug for u du by dx v du by dy d square u by dy square and g beta into T wall minus T infinity, you can write this in terms of Grashof number again, right. So, what this will be in terms of Grashof number? So, your Grashof number once again g beta T wall minus T infinity into x cube by nu square. So, this will be simply Grashof number x by x cube into nu square theta. So, please plug in the other terms, you will get some terms cancelled, some terms will cancel away, and tell me what will be the final equation. Will you be able to transform the PDE into a ODE function of eta? Okay. As you keep doing, I will also write down the energy equation. So, the energy equation can also we can use the differentiation by parts here. So, you can write this as, you can assume now theta to be only a function of eta. Now, let us use the variable theta of eta here. Okay. So, when you plot this non-dimensional temperature also as a function of the similarity variable, they should all collapse, same way like your u by u reference. Okay. In that case, then theta will be only a function of eta. So, we can split this as d theta by d eta into d eta by dx and so on. So, I will give you the final similarity equation here. This comes out to be d cube f by d eta cube plus 3 times f into d square f by d eta square minus twice df by d eta whole square plus theta equal to 0. So, finally, we have successfully transformed PDE into ODE as a function of only eta, and Now you see we also have the theta term here. So please note that finally when we are solving this equation by shooting method, we have to make sure we solve both the momentum and the energy equations simultaneously. Okay. So this is where the coupling comes from. So you can compare this to the Blasius equation. So there we had d cube f by d eta cube plus we had f by 2 into d square f by d eta square, the other terms were not there. So compared to that we have now additional terms. Okay. So to complete it, now we can also transform the energy equation as a function of only eta by substituting for u v d eta by dx, d eta by dy and so on. Okay. So I will again give you the final similarity equation for energy, d square theta by d eta square plus so you get d square theta by d eta square plus 3 times Prandtl number, where Prandtl number is the ratio of momentum to thermal diffusion. So in the case of Polhausen's solution for flat plate external forced convection, there was PR into f by 2. So now we have modified this. Okay. So tomorrow we will stop here. You can also go home and verify whether you are getting the final equations. So tomorrow we will apply the boundary conditions and then look at the application of shooting, that we will develop the expression for Nusselt number. All right. Thank you.